Okay, let's talk about our third type of series called the p-series. These p-series are very important because they are heavily tested on the AP exam. The definition of a p-series is the following. It's a series in the form of 1 over n to the p, where n is our counter, so we start with n equals 1 and go up to infinity, and p is the exponent, and p has to be a real number. A special case of the p-series is the harmonic p-series, which is where p equals 1. So you're summing the expression 1 to n from n equals 1 to infinity. So you're adding up 1 plus 1/2 plus 1/3, etc. So we want to know whether the harmonic series of 1 over n converges, and we want to know whether the p-series with p equals 2 converges. And we can relate these back to improper integrals that we studied back in Unit 6. And I can actually take a look at the improper integral from 1 to infinity of 1 over n dn. And I know that to evaluate that, I'm going to have to take a limit as t goes to infinity of the integral from 1 to t of 1 over n dn. Then I will integrate 1 over n, still have my limit as t goes to infinity. The integral of 1 over n is the natural log of the absolute value of n from 1 to t. And then I need to evaluate that first at t, so I have the ln of the absolute value of t minus the ln of the absolute value of 1, but the ln of 1 is 0. So the natural log of the absolute value of t as t goes to infinity is infinity, and therefore this improper integral is divergent, which means that the harmonic p-series does not converge because it behaves the same way that its related improper integral behaves. So let's take a look at 1 over n squared, and I will go ahead and set it up as the limit as t goes to infinity of the integral from 1 to t of 1 over n squared dn. And when I integrate 1 over n squared, I go to negative 1 over n, and I'm evaluating that from 1 to t. Now when I plug in t and then 1, I have the limit as t goes to infinity of negative 1 over t minus a negative 1 over 1. And then as t goes to infinity, I find that my limit here is 1. So yes, this p-series converges because its related improper integral converges. So what are your guesses for what values of p the p-series will converge? Well, it's the same as with what we called the p-integral, or the improper integral that is of this same form. The p-series converges when your p-value is greater than 1 and diverges when your p-value is less than or equal to 1. So now we want to talk about why. Why does 1 over n squared converge while 1 over n does not? So there are proofs that you can look at. If you go to YouTube or Khan Academy, you could find some proofs of this. But if you think about 1 over n, this is the harmonic p-series. Here are all the terms. What's interesting is that if you take a look at, ignoring this first term, if you look at 1/2 and then you add these next two terms, if you add these, you get out 7/12, which is larger than 1/2, right? Then if you add these four terms, you're going to get some fraction that is also larger than 1/2. And if you add these terms, you're going to get some fraction that's larger than 1/2. So each of the groupings will be larger than this grouping, in which case the series continues to grow. And I actually have another proof of that I'll show you here. Basically, this is the harmonic p-series for the first 16 terms. Okay, let's replace some of these terms with smaller numbers. So for example, instead of 1/3, let's replace that with 1/4. Instead of 1/5, 1/6, and 1/7, let's replace each of those with 1/8. Do the same thing for 1/9 through 1/15. We're going to replace them all with 1/16. Then we see that these two add up to 1/2, these 4 add up to 1/2, and these 8 add up to 1/2. So here's the deal. We know this series diverges because if we're adding 1/2 consistently, we add to infinity. And so our series is actually larger than this series, so it must also diverge, because remember that 1/3 is larger than 1/4, and 1/5 is larger than 1/8. So when we replaced some of our numbers with smaller numbers, we proved divergence, or we showed divergence. So if we are larger than a known divergent series, our series must also diverge just by common sense. Now, this one, if we look at 1 over n squared, we can group the terms after this first term no matter how we like. We could look at the first term and then the next two, and then we could look at 4, and then we could look at 8. And what would happen is no matter how we group them, every time we add up more terms, we're going to get out a number that is smaller than 0.65. And so each grouping, because it's smaller than a given number, these the total sum actually will converge on an exact number. And if you want, like I said, if you want more proofs of that, go ahead and look for it on YouTube or Khan Academy.